All right, hello everybody. So first of all, thank you so much. I recently was informed that I now have gone over 1,000 subscribers. Never thought I would have that much reach when I first started doing this. Maybe at some point I'll make a, about me video and tell you why I started this channel and how that all came about. But thank you so much. I get emails from people almost every day now, from all over the world saying that my videos have helped them, or they get some sort of value from them. And people are finding me on LinkedIn, and I'm there obviously if you want to connect with me. So thank you, just very flattered. So I thought this would be a good 1,000 subscriber special video, and that is how to make what's called a tilt map, or maybe more colloquially you could call a tilt cheat sheet. So that's what you're seeing in front of you right now. So what exactly is a tilt map? Well, a tilt map is something that you can use to tell you how you need to tilt the stage to align a single crystal with the zone axis, depending on how the diffraction pattern appears. So if you look at the finished tilt map that we see right now, and I'm going to show you how I got to this, we will derive this actual tilt map. So in the middle, you see, you see 5 diffraction patterns. So in the middle, you see the diffraction pattern if the zone axis alignment was perfect. Okay, and this is a simulated diffraction pattern for just a cubic, I believe, simple cubic crystal. That would be another video, of course, how to do these simulations, but for now, just try not to worry about that. But anyways, right in the middle, that's obviously perfect zone axis alignment. And then we have 4 other diffraction patterns. You can see obviously the direct beam in each one. Okay, that's obviously the center of the pattern. That's where everything's relative to. So if we look at the pattern that's at 12 o'clock, okay, so the top one, you can see that I have basically an arc of a Laue circle, which I've talked about in a previous video about zone axis alignment. You can see basically though that the spots in the pattern, they're curving downward. Okay, if I go down and to the right, okay, the pattern that's at 3 o'clock, I see the spots are curving to the left. And if I go to the one at 6 o'clock, the spots are curving upward. And then if I see the pattern over at 9 o'clock, the spots are curving to the right. So each of these 4 patterns has associated with it an instruction that says basically how you need to tilt the stage to get to the on-axis pattern that you see in the middle. Okay, and so this is what I have termed a tilt map or a tilt cheat sheet. There isn't actually an official term for this. This is just something that I've made up. I've actually never seen anybody derive one of these. This is actually the first time, so maybe I'm taking credit for that. But this is very useful, so you're not just kind of guessing when you're trying to do zone axis alignment and you're trying to get like a high-res image or a STEM image, and we will go over both of those. So I'm going to show you how to derive one of these maps, and it's actually not terribly difficult to do, believe it or not. And once you do it, you'll probably never have to do it again, and you'll have it there, and you can just keep it with you with the microscope, and you will always know how to tilt to get to where you want to go. I will stress that the tilt maps, of course, do depend on a lot of variables. They depend on your microscope. They depend on, depending on your system, what voltage you're at, what camera length you're at when you're viewing the diffraction pattern as well. So keep that in mind. And I will address those as well as we derive this map. So without further ado, let's get to the actual map derivation. All right, so we have microscope control here, and I have a single crystal of silicon with some films on the top. So the single crystal is that left side of the specimen over there where the cursor is pointing. And so that's what you need to do this. You need a single crystal specimen to create this map. So I'm going to move where I basically have the entire field of view is a single crystal, and then I'm going to go into diffraction mode. And you can see here I'm not on the zone axis. Okay, clearly I have a very distinct Lowy circle. I'm just going to play around with the FluCam settings here, but you can see very clearly I'm not on the zone axis. Okay, so step one of deriving the tilt map is that you've got to get to the zone axis to begin with. Now don't worry about how you got there initially, just get to the zone axis. Don't worry about what you did to do it. But you have to start from what you're seeing here, where you have basically perfect zone axis alignment. And then once we get to this, then we can figure out what we need to do to tilt a certain way. Of course, since I tilted, I'm going to reset eccentric height. I went back into image mode, and I adjusted my Z coordinate of the stage to refocus the image. And you can see here I am on the zone axis. And so again, this is what this corresponds to in our tilt map, right? Is that central diffraction pattern of the 5 diffraction patterns, which is again when I'm perfectly on the zone axis. Okay, so we've got one piece of the tilt map created. So now what I'm going to do is adjust alpha in the positive direction and then take a look at the diffraction pattern. So you see here I'm no longer on the zone axis, and my Lowy circle is curving to the right. And again, to do that, I adjusted plus alpha. So based on this, based on the appearance of the pattern, I can now add a piece to my tilt map. And this is what it looks like. Okay, so if my diffraction pattern looks like this, my Lowy circle is curving to the right. The spots are curving to the right. I have to adjust minus alpha. Okay, because remember, I adjusted alpha in the positive direction to get this. That means if it looks like this, I have to adjust alpha toward the negative direction. Okay? All right, so that's one more piece of the tilt map. So now I'm going to adjust alpha in the negative direction. You see we get back to the zone axis. And then if I keep going, you're going to see here that the spots curve the other direction. Now they curve to the left. So now I can make another piece of the tilt map. Okay, so now I've got my spots curving to the left. Okay, this means that I have to adjust alpha in the positive direction if I want to go back to the zone axis. Okay, all right, hopefully everybody's following me right now. So I've got the alpha tilts covered at this point. So now we're going to move to the beta tilts. All right, so returning to the diffraction pattern, I'm going to go back to the zone axis. And again, I need to go plus alpha to get back. And now I'm going to go and adjust the beta tilt. All right, so which one do I adjust here? All right, so I'm going positive beta. And now you see the Lowy circle is curving up. Okay. Now again, if you adjust, what I'm doing here is I'm going back into image mode and I'm just resetting the height. Especially if you adjust the beta tilt, your height's going to go off because it's not eccentric in beta. And then I'm going to head back into diffraction mode, and it still looks basically the same. Again, your area of interest might move, so you have to recenter it. But you see now I have the Lowy circle curving upward, so I can make another piece of the tilt map. All right, so if my Lowy circle is curving up, because I adjusted beta in the positive direction, that means if my Lowy circle is curving up, I have to adjust towards negative beta. Okay, so if your diffraction pattern looks like this, go to the negative beta tilt control. All right, so there's just one more piece of the puzzle, and by now it should be obvious what that is. All right, so you can see I'm going to go back to the zone axis. I'm adjusting beta towards negative. You can see beta is getting smaller, and then I'm back to the zone axis. And then if I keep going negative, I should see the Lowy circle curve downward, which it does. All right, so I've got the last piece that I need to complete my tilt map. Okay, so if your Lowy circle is curving down, you need to adjust positive beta tilt control. Okay? All right, so we've got all the pieces of the puzzle now. So I showed these in isolation rather than all at once to create the final tilt map. And just to make sure that we're all sane, if I adjust beta positive, you can see that we do indeed go back to the zone axis. So we are entirely self-consistent, just like we would hope to be. And so now we can make the final tilt map or cheat sheet. And this is what it looks like, which is exactly what I showed you at the beginning of the video. All right, so I don't know if you were paying attention or not, but I did all that tilt map generation at camera length of 410 millimeters. So now what I'm going to do is I'm going to drop the camera length to 77. The reason I'm doing that is there's actually a cutoff at which point the pattern rotates by 180 degrees. So that was actually deliberate. And I'm just playing around with the FluCam settings here, but you can see we're on the zone axis. But what I want to show you now is, okay, so I adjusted alpha in the positive direction, and now my Lowy circle is curving to the left. Okay, so in that case, I had to go alpha negative, and in this case now, my circle's curving to the right, I have to go alpha positive to get back to the zone axis. I can do the same thing with beta. Okay, so you can see here now I adjusted beta positive, my circle's curving down, so I have to adjust negative beta. And again, if I keep going negative beta now, I should have the Lowy circle curving up. Okay, so you can see now I'd have to adjust beta positive to get back to the zone axis, which I'll do here right now. So what you find is if your indicated camera length is less than 89 millimeters, and again, this is unique to this particular microscope. Oops, sorry, I meant 98 millimeters. I think I might have said 89 earlier, but it is 98 millimeters. That is the cutoff. If you are below 98 millimeters, your tilt map is actually rotated by 180 degrees relative to the map that we just generated. Okay, so there's two different tilt maps depending on what regime of camera length you are using to view your diffraction pattern and do your zone axis alignment. That's why it's usually kind of the best practice to like pick a specific camera length and just work based on that, especially if you're dealing with older systems where you might have a different rotation for literally every camera length. On newer systems, you usually don't have that problem, but that just goes to show you that the tilt map can have some dependence on the camera length that you're using, can also have some dependence on the voltage. I'm obviously only deriving this for 200 kV operation. So now we're going to talk about STEM mode. So just really quickly here, I'm setting the system up for STEM mode operation. I applied the FEG register for STEM mode, and now I'm heading into STEM mode, and I will very quickly here run through the stem alignment. So one of the things I'm going to do here just for demonstrative purposes is I'm going to change the FluCam to high resolution mode. That just magnifies the FluCam image a little bit more. And then I'm going into the beam tab and I'm setting the spot size just higher than where it was. It was at 1. I'm not trying to really do any stem imaging here. I'm trying to show you how the tilt map works in STEM mode, which is basically identical to how it works in conventional mode. The only real difference is the appearance of your pattern. But we'll go through the stem alignment here anyway, because again, people ask about that. So I've gone to the biggest C2 aperture that I can find, And I'm going to have to play around with my display settings here. And I'm defocusing until I can see an image of the sample. And I should have done this before, but I'll bump up my camera length because it's going to make it easier to see the image in the ronchigram. There we go. And obviously you want to do this over something that is mostly amorphous. I've got some E-beam deposited platinum from our dual beam instrument, which is that stuff right there. And that works great for doing this. So you can adjust your focus till you start to see rings. Perfect. All right. So right here, this is what you want to start from. First thing I'm going to do is make sure the rings are circular. They weren't terribly off to begin with. And now they're basically perfect. So I'll go ahead and turn off the condenser stigmators. And the next thing is rotation, center, intensity, and direct alignments. Sometimes when you do this, I've noticed there's a shift in the image, so you have to turn it off, hit done, and then go refine it for your area. And then when you turn it back on, it shouldn't move. I don't know why it does that. It's just kind of an annoying quirk. All right, so you're looking for how does the ronchigram expand while you change the focus. So you want the ronchigram to expand straight in and out. You're not really concerned with where the ronchigram is inside the condenser aperture so much. You're really just concerned with how it's expanding. So it looks pretty good right here. Tried to kind of throw it off deliberately at the beginning. So you're adjusting your multifunction knobs right now. And then periodically you're adjusting the focus to make sure that it's expanding and contracting concentrically. So you can see right there, it's definitely off. I did that deliberately. And that looks really good right there. And you can select done. And then the next thing is put in the optimal aperture to give you the optimal semi-angle of convergence for your beam. In this system, it happens to be the 70 micron C2 aperture, and then you just want to center it around the middle of your ronchigram. So this is off just a little bit, but not too much. And there we go. It's basically perfect right there. And you can deselect adjust once you have that aperture centered, which I should be doing here momentarily. There we go. And then I'm going to go back and drop my camera length down to something suitable for a HADF image. So 98 millimeters is what I'm going to use. So again, remember in conventional mode, we said that 98 millimeters was the cutoff. If I go below 98 millimeters, I have that 180 degree rotation in the tilt map. Okay, so I'm going to play around with the flue cam here a little bit. See if I can make my diffraction pattern a little easier to see. It's a little bit overexposed, but that's okay. And then we'll go to Velox here. All right, so there's my single crystal of silicon on the left, and you've got some layers on the top. So again, you need to be in a single crystal here because we're going to basically generate the tilt map. We're going to do it in stem mode. Okay, so there's my beam position marker. I can stop the scan, and then if I go back to the flue cam, okay, sorry, it's a little tricky to do with one monitor. Drop the exposure time down. All right, so you can see right there, I'm basically on the zone axis right now. So we can do the same thing that we did before in conventional mode. So again, I'm adjusting alpha in the positive direction. So you see I have the Lowy circle again, it's curving to the right. You can also change the view mode to grayscale and temperature depending on your preference. I usually just like the grayscale, but sometimes the temperatures works well for some applications. But you see I have the Lowy circle curving to the right. Okay, this is just like what we saw in conventional mode. The only difference now is that I have a convergent beam, so I have a seabed pattern rather than focused spots. Okay, so basically the map that I generate by working in STEM mode is no different than the map I generated in conventional mode. So you can see here now I've gone too far negative with alpha, and my rings are curving to the left, so that means I have to adjust alpha positive. Okay, this is just like, again, the same thing that we found when we generated the map in conventional mode. So really quickly, we can do the same thing for the beta tilt. So I'm going to increase beta positive in the positive direction. Especially if you adjust beta, you're not going to be at eccentric. So I'm going back into the STEM image and I'm refocusing with the Z. So this can be frustrating sometimes, especially in STEM mode, if you're trying to get like one spot along zone axis, because when you tilt, the spot's going to move. So you're going to have to stop the scan, reposition the beam, check the seabed pattern, refocus with the Z, and this can be irritating and frustrating, but the result will be well worth it. So you see spots are curving up. That means I'd have to tilt beta in the negative direction. So I tilt beta in the negative direction, my spots curve down. So that means I have to tilt beta in the positive direction. This is exactly what we saw with the tilt map in the conventional image. So it's no different in STEM. The only difference is that now you have a seabed pattern as opposed to a conventional pattern. Okay, and again, because the image was frozen, right, that was wherever the beam position marker was located, which happened to be there at the moment. So if you want to take your STEM image there, great. If not, you'd have to position it and adjust accordingly. All right, so this is what the final tilt map looks like. You can see it's very similar to what we saw with the map we generated in conventional mode. The only difference now is how the diffraction patterns appear. So now we have disks because we have seabed patterns, but the curvature of the disks is identical to what we saw previously. Okay, these are again obviously simulations. This was done with software called MuSTEM, which is free. You can find this if you search for it. It's fairly easy to use. But the only caveat, of course, is I'm operating in that same indicated camera length regime. This is 98 millimeters indicated or higher. Again, unique to this specific microscope. And that, in a nutshell, is how you generate a tilt map or tilt cheat sheet. So thanks for stopping by to watch. Hope you found this video useful or helpful for you. If you haven't subscribed, please consider subscribing. It would mean a lot to me. If you know somebody who would find this video useful, please feel free to share it with him or her. I'd love to hear topic requests. Obviously, I do have a full-time job in addition to this, so I can't just make YouTube videos full-time, which would be nice, but I can't do that, unfortunately. But I'm always looking for a way to sneak a couple in here and there. And so with that, if you have any questions or comments, please let me know, and look forward to seeing you again in the next video.